Welcome back, friends, to another lecture on quantum mechanics and the relativistic regime. So, we have been looking at various aspects of the Dirac equation. We have finished the Klein-Gordon equation, and then we started looking at the Dirac equation. And in that process, we have been trying to understand what these wave functions are essentially, because these I call them as spinors, and then I went to group theory and then introduced the unitary groups and said unitary groups are essentially have representations in terms of spinors and so on. So, and then we went with the Lorentz transformations, and then we started looking at Lorentz transformations as a group, and then we looked at the classification of the Lorentz transformations, and then finally we ended up with the what are the representations of the Lorentz transformations. Yesterday we looked at the last class we looked at transformations with respect to how does a scalar transform, how does a vector transform, and so on. So, essentially now at the end of the last lecture what I mentioned was that this was uh, the algebra of the Lorentz group. So, you have the boost which go into a rotation, and the rotations are closed within themselves, they do not go they can form a group on their own, they form a closed algebra on their own, and then a boost and a rotation goes to a boost essentially, which you can see in this commutation relations, which you can, and it would be nice if we can play around with these commutation relations, take examples, start with one particular case of take say for example a rotation in xy direction and a boost in say z direction, and then see what happens to the boost. Essentially this would be extremely nice exercise to look at. This should be equivalent to a boost in another direction essentially. So, this would be really nice if you can verify this thing on your own. Okay. So, then we went with the general Lorentz transformation. How do we write down? And then we wrote down Poincare group, Poincare transformations, and Poincare group. The group of Poincare transformations is called Poincare group. So, the group of Poincare transformations is called Poincare group. So, this is a bigger group compared to the Lorentz group, and technically what we said was that we can construct all one particle states, that is a language of quantum field theory, in which you can show that each particle which we observe in nature is a representation of the Poincare group. Okay, we will not go into all those details, essentially we will not go into the details, but we are only interested in how the Lorentz group transformation, how various wave functions transforms under the Lorentz group essentially. So, we showed that how a scalar transforms. Scalar is invariant, which is a wave function of the Klein-Gordon field essentially, and then it does not have any index, and phi is invariant under Lorentz transformation. So, it is very easy to show the invariance of the Klein-Gordon equation essentially under Lorentz transformations, because it is just a scalar equation, and so it is always invariant under Lorentz transformations. You can explicitly verify that there is an upper index here and a lower index here, and you take a Lorentz transformation on each of these terms in your Klein-Gordon field, and then you can show that this is invariant under Lorentz transformations. What about a mu? A mu is just a vector potential, also the photon particle essentially, or the photon wave function. Okay. So, this we have seen. This is the field of the electromagnetic potential essentially, the electromagnetic field essentially, or this is the scalar potential, and this is the A bar is the vector potential of the electromagnetic field. And you see that the A mu transforms exactly like any 4 vector, like x mu, p mu, j mu, or so on. And so that's not a problem. So meaning we can show we are not looking at the wave functions of the A mu. We will at some point we'll look at it. The wave functions of A mu are the solutions of the equation. I think I mentioned some time ago in one of the lectures, that is equal to Maxwell, L Maxwell is equal to minus 1 by 4 f mu nu f mu nu, and these are the wave functions of this particular equation. Essentially are the solutions, the wave functions are solutions of this particular equation. The wave functions are solutions of the equations of motion of this particular Lagrangian. Sorry, I should be more careful. This is the Lagrangian of the Maxwell fields essentially, and then you get the solutions of this particular equation to be 0, and this is the equations of the A mu field. Essentially the A mu field satisfies this equation, which is given by this particular fashion. Okay. Now this is also easily to show that this is this A mu is not an invariant quantity, but it transforms like a vector. Okay, it transforms like a vector under Lorentz transformations, essentially like p mu, x mu, j mu, etc. Now, so the question then come about what about psi, the Dirac wave function. We have looked at the Dirac wave function, which is a solution of the Dirac equation, and we said that this transforms as a spinor under Lorentz transformations essentially. Okay, we made this comment and we called it as a spinor. And what is a spinor essentially? What is a spinor? That's what the question we have been trying to answer, and we have been going in circles and various ways essentially. So the simplest thing is to start with saying that okay, it transforms as a representations of the Lorentz group in a spinor vector space. So spinors form a vector space, and the group spanned by the spinor vector space is called depends on the group, like unitary groups or Clifford algebra or so on, so essentially. But we don't have to worry about the detailed mathematical structure, but what I want you to emphasize appreciate is the fact that let's take one mathematical fact and then we'll build upon it essentially, then things becomes easier essentially. So SO31 is the group of Lorentz transformations, and this is C is isomorphic to SU2 times SU2. It's a direct product. This is something called a direct product of two SU2 groups and Z2 modded by Z2. I'll tell you what a Z2 is. Essentially Z2 is when Z2 is a group of two elements, which is Z2 is a discrete group two elements is nothing but plus 1 and minus 1. So there are only two elements in this group essentially, which is plus 1 and minus 1. So what does the Z2 modding by Z2, what does this representation tells you is that you have to this representation tells you that the representations of this particular direct product have to be modded by Z2. That means they have to be separated by the imposition of this particular discrete group. Okay, now we don't have to go on to all the technical details. This it will end up being essentially the Z2 is roughly end up being parity essentially. Okay, the space inversion, but anyway we will worry about how does this essentially does Dirac-Spiner form a representation of the Lorentz group? Now let's look at this. Let's imagine that somebody gave you this equation, or some mathematician told you that SO31 is isomorphic to SU2 times SU2. So the representations of SU2 are also representations of the Lorentz group. This particular right hand side, essentially SU2 times SU2 direct product is equal to, forget about Z2 for the time being, we will come back to it a bit later by the modification of by the modding of the Z2. Okay, this operation is called modding, but let's forget about it. It's a direct product of two SU2 groups essentially. So SO31 is isomorphic to direct product of two SU2 groups. So that means SU2 groups have essentially representations of spinors. So they are two component spinors. So direct product of two component spinors would end up being a 4 component spinor. So you end up having a representation of the SU2 doublet, essentially SU2 doublet times SU2 doublet. Okay, a representation of the SU2 product group of SU2 should be a representation of the Lorentz group. That is the reason why there is a spinor representation of the Lorentz transformations essentially. Okay, because of this reason, okay, because of this reason there is a direct there is a spinor representation of the Lorentz group. So consider, so this is how we answer this question essentially. So now we are in the question we started with can be answered. So I assume that you all know what a direct product is, so that if you have two matrices, say for example say A B C D, direct product E F G H. So the direct product, this is a 2 by 2 matrix and this is a 2 by 2 matrix. The direct product would be a 4 by 4 matrix in which every element is multiplied by E F G H B times E F G H C times, okay, E F G H and D times E F G H, and this you see that this will end up being a 4 by 4 matrix of this particular type, because once you expand that our lower 2 by 2 block, essentially it will give you a 4 by 4 block, but everything is multiplied by everything. Now the generators, now let's look at the generator level essentially. Okay, the generators of SU2 are sigma matrices. Now you should remember the way I am proceeding in this lecture is trying to it's a sort of heuristic way. I am not let's not try to be mathematically completely rigorous, but try to understand the physics behind it, essentially what is exactly happening. Okay, now we can make it mathematically more rigorous, but at the end of the day if you get the heuristic argument, then we can go into more mathematical detail essentially, but that is not required for this present set of lectures, because the present set of lectures are not really forming the this is enough background to start with understanding more details about say for example when you go into the field theory language, essentially the quantum field theory, which is a more accurate theory of relativistic quantum field theories, quantum mechanics essentially. Now so what you have is SU2 times direct product SU2 is essentially the generators would be direct product of sigma matrices Now, have you seen the direct product of sigma matrices somewhere? Have we seen them somewhere? In the course of lectures? You may not have seen them as direct product themselves, but you have seen them somewhere essentially. Now, you have actually seen them in gamma matrices. The gamma matrices, the Dirac representation of the gamma matrices, gamma mu is 0 sigma mu sigma. If you remember, I think I'll just pull out the lectures. I think we have done it here, somewhere here, beta alpha matrices, here it is. So, gamma I matrices, gamma 0 is equal to beta, and gamma I is nothing but beta I times alpha I essentially. Okay. So, you can represent them, okay, in this particular fashion. Okay, let us remember that the sigma matrices. Okay, I should put it in this particular fashion to be consistent with our notation. Okay, and gamma 0 is also there, which is nothing but okay, let me write it as beta. So, you see, what you see is that the gamma matrices form a representation of the Lorentz group, because your sigma matrices are essentially the direct product of sigma matrix. This you can write it as a direct product of say 1 times sigma I, essentially direct product of 1 time 1 by 2 by 2 times sigma I. So, this is nothing but 1 times sigma I. Okay. So, this gives me your gamma matrices essentially. So, you can in principle construct all your gamma matrices at various orders essentially, at various ways, and okay, 1 times sigma I is a direct product essentially, okay, of 1 times sigma I gives you the gamma matrices of this particular type essentially. This is your gamma matrices. So, the gamma matrices form a representation of the Lorentz group. Now, why there are no 2 sigma matrices, we will come back to it, meaning you cannot, why it is not direct product of 2 sigma matrices. It is not exactly direct of this, but this is just an indication. Let me not put it this way, but this is true that as you go to higher and higher dimensions, this is the way we build the spinor representations for higher for various dimensions of space time essentially. So, the various dimensions of space time, we take them as sigma matrices and take the product of them. Essentially, if you are going into 6 dimensions, so you take direct product of 3 sigma matrices and so on. So, essentially, okay. So, the gamma matrices form a representation of the Lorentz group. How do they form? Because you can think them as, so for example, you can write them as a representation of the Lorentz group by defining what your the transformation is essentially. So, what we wrote down, your transformation so how do they form a representation of Lorentz group? Essentially, that they form a representation of the Lorentz group by considering. So we have started with lambda is equal to I plus 1 by 2 omega mu nu m mu nu essentially. Okay. Okay. Now omega mu nu is epsilon mu nu, right? Essentially epsilon I 0 I. Essentially we wrote it down. So epsilon I. So omega mu nu. Okay. Let's keep it as omega mu nu. Okay. Now by forming a representation of mu nu, by forming a representation of mu nu, the gamma matrices really form a representation. So you end up, okay. So you exactly in the same form we can write as S is equal to Lorentz transformation for spinor space for spinors. So the Lorentz transformation on the wave functions, okay, on the wave functions of the Dirac spinors S of lambda is equal to 1 minus I by sig 4 sigma mu nu epsilon mu nu. Okay, or to make the notation consistent we can write it as, okay, omega mu nu sigma mu nu, where sigma mu nu is equal to gamma nu with a factor 1 by 2 essentially. Okay. Okay. So now we came in the roundabout way. Okay, we came in the roundabout way by arguing that the generators of the generators of the Lorentz transformation are essentially your mu nu or boost and generators of boost and rotations. They will appear slightly differently in a representation of gamma matrices and gamma matrices form a representation of a Lorentz group because there is a representation of boost and rotations in a completely different wave function in a completely different vector space, which is the spinor vector space, in terms of the sigma matrices or the gamma matrices. So what you are looking at, okay, what you are looking at is a representation of the Lorentz group. You are looking at a different. So the Lorentz transformation is not exactly the same way as it transforms. Okay, the Dirac wave function doesn't exactly transform like a vector or like a scalar. So it is not so obvious. Essentially, it transforms as a representation. And what I tried to show you is that how the gamma matrices would form a representation because of the isomorphicity between the Lorentz group and SU2 times SU2 essentially. Okay, now this is sort of answers our question. We told that why a Dirac spinor becomes a representation of the Lorentz group essentially, but let's make it more accurate essentially more how does explicitly the Lorentz transformation appear on a Dirac spinor? This is, I wrote it down already, but let me write it down in more accurately essentially on a Lorentz spinor. I hope now you are convinced that the spinors form a representation of the Lorentz group because of this connection I showed you essentially. The spinors form a representation, but explicitly how do they transform? The spinors do form a representation. So how does LT is Lorentz transformations. How does a Dirac spinor transform essentially? So normally how does it transform? Let's see. So the Dirac spinor is covariant under um, Lorentz transformations essentially. I should be more accurate. Essentially, I shouldn't say the Dirac equation. Dirac equation is covariant under Lorentz transformations. So what does it mean? It's not invariant. It's covariant. The form of the Dirac equation doesn't change. So the form is essentially del mu minus I del slash minus m psi. This form becomes this form is invariant, but what the form invariance is called covariance essentially. The form invariance is called covariance. So what we will look at is the covariance of the Dirac equation in the next this lecture, the remaining part of this lecture and the next lecture. And so with this we will be convinced that the Lorentz transformations, this first, that the spinors form a representation of the Lorentz group, and the how does the Dirac spinors transform under Lorentz transformations. Okay. So let's start with x mu. How does x mu transform? X mu prime x mu prime is equal to lambda mu nu x nu. So psi of prime goes as psi prime of lambda x, that is equal to sum x of psi of x. So psi is a representation of the Lorentz transformation. Psi is a representation of the Lorentz transformation. On the spinorial space. Okay, on the spinorial, in the spinorial space, psi is a representation of the Lorentz transformation. Now we say that the form of the Dirac equation should be completely invariant essentially under the modification of the under the modification of the under Lorentz transformations. Why there is no modification? So okay, so what we have is that I del mu gamma mu del mu minus m psi of x mu is equal to 0. So the same thing I should write down the form in a Lorentz invariant transform. So let me choose another index. So nu prime minus m psi prime of x prime of nu should be equivalent to 0. This is LD. So this is after Lorentz transformation, the form should look exactly in this particular fashion. So it should have the same form as the original Dirac equation essentially. Now this would mean that using this condition, that how does Dirac equation transform, because I can use the S here. So I can use what is psi prime and everything essentially, okay, for the psi prime. So this would mean that I S gamma mu S inverse del mu S psi minus m psi of x is equal to 0. Okay. Now this is equivalent to I S gamma mu S inverse del mu prime psi prime minus m psi prime of x prime is equal to 0. So I have not I have re-expressed both the equations in this the nu prime essentially in terms of S inverse S. Now the point here you should remember is that the gamma mu matrices, okay, the gamma mu matrices also okay, where del mu prime is equal to lambda nu prime mu prime del nu prime. Okay, this is the assumption I have made. Now the point is that remember this is very important, that the gamma matrices should also satisfy some condition. The gamma matrices should also satisfy this condition that under Lorentz transformations or on the representation of lambda under the Lorentz transformations, they should be invariant. Okay. So this condition from 1 and 2 will appear as so gammas are not they are four component spinors essentially. Okay, they are not spinors, they are matrices, they are 4 by 4 matrices, there are 4 of them. Under the Lorentz transformation they transform as S gamma mu S inverse lambda nu mu, and only when this is equivalent to gamma nu the first and second equations are the Dirac equations remain, the form of the Dirac equation remains invariant essentially. Okay, the form of, so what we want is the Lorentz transformed version should remain the same part as this one. Now substituting for the S part essentially, because of the delta mu nu part, del mu nu part, mu prime part, what you see is that unless this is satisfied, unless this condition is satisfied, this will give you a lambda mu nu. This lambda mu nu is coming from the del, and S inverse gamma mu S inverse, unless this is lambda mu nu is equal to gamma nu, that means under the Lorentz transformation this condition should be satisfied. That means that gamma mu form should remain should be invariant essentially. See why this should be this condition is appearing is, again go back, the gamma mu matrices carry non-trivial representation of information about rotations, and they are representations at the end of the day of the mu nu matrices, which are essentially the representations of the generators of boost and rotations. So the gamma matrices contain non-trivial information about boost and as well as rotations. Okay, and that is the reason this condition should always be valid, such that you remain the form of the form of the equation should be the same under Lorentz transformations. Okay, this is the condition we imposed, and this condition gives the condition this condition gives you this you can see simply with simple algebra just by making use of this particular relation which we have used, essentially psi prime of x prime is equal to S of psi of x. Essentially putting it back into the Dirac equation, you will end up having this condition that the gamma matrices also should give you this particular thing. Now given this, we want to know what is S essentially, such that this is always satisfied. What is S? Anyway, we have already seen the answer of S essentially. S is nothing but, okay, S is nothing but okay, sigma mu nu is I by 4, I by 2 essentially. I wrote it as I by, yeah, it's 2. Yeah, it's, I think I wrote it earlier also as I by 2. Yeah, it's, this is I by 2. I by 2 gamma mu gamma nu. And that's it. And so if you have this form, this remains valid, and the Dirac equation is covariant under Lorentz transformations. Okay. Now this is wonderful. This is amazing that what we have achieved essentially that. Okay, I tried to get you. Okay, so this form. Okay, what we have achieved today is amazing that if I try to get an expression for S or the representations of the Lorentz group on spinors by guessing that given this relation, okay, given this relation as a direct product of two SU2s, so it should be some form of gamma matrices. We said that it should be, we made a guess, okay, made a guess that it should be gamma matrices because gamma matrices we know are direct product of sigma matrices essentially. So giving that guess essentially we then said that then we said that there could be a representation of the Lorentz transformation in a spinorial space in terms of gamma matrices, which whose infinitesimal thing is like this, infinitesimal, okay, whose infinitesimal transformation looks like this. Now we went further, okay, this is one step, but we went the other way around. We said that okay, how does a Dirac spinor transform under Lorentz transformations? So we went the other way around. This is all this we achieved with a lot of work, essentially understanding Lorentz group, Lorentz transformations, all the group theory, unitary groups, all that stuff essentially, and then we achieved that this guess that the Lorentz transformations should have gamma matrices as generators of Lorentz transformations on spinorial space. Up to here we received. Okay. On the other hand, if we start with the Dirac equation directly, okay, we did, okay, and ask the question, how does a Dirac spinor transform under Lorentz transformations? And let's put let's not say what it is essentially, just let's say that it is some S. Okay, S is some representation of the Lorentz group in spinorial space. The only condition we insisted is that the Dirac equation should not change its form. The Dirac equation should remain the same form under Lorentz transformations. Under Lorentz transformations, that condition is called covariance condition of the Dirac equation. Okay, the form remains same. Now imposing this condition, we end up having a condition which is different, which is essentially saying that this condition should be valid. So the gamma, the condition on gamma matrices should be valid essentially. Now the condition on the gamma matrices is valid only when S has a very specific form, and that forms is again in terms of the sigma in terms of the gamma matrices. When the gamma matrices have a very specific form, this condition is always true, and so we can see that by two ways. Okay, again we can do the infinitesimal transformation essentially for Lorentz, the full finite transformation. So the finite transformation of S is of this particular the Lorentz transformation is this particular form, and where again you see this particular gamma matrices appearing as the representations of mu nu. Mu nu are your omegas are your epsilon, the omega are your tiny rotations and tiny boost, and the generators are your sigma mu nu, and representations of mu nu are gamma mu and gamma nu in the spinorial space. In the spinorial space. So now I hope that you are convinced that the Dirac spinors form actually a representation of the Lorentz transformation. Okay, this is the something which we asked a few classes ago. How do we convince ourselves that these form a representation of the Lorentz transformations? And what we have seen is that yes, they do form a representation of the Lorentz group, and they transform in this particular fashion. Of course, there are some mathematical details which we had to go through, and the essential point is that essential point is that there are two essential points. One is the connection between the Lorentz transformation and the SU2 times direct product of SU2 is essentially SU2 times SU2 by Z2 essentially technically, and the second connection is second important point is that the Dirac equation should be covariant under Lorentz transformations. These two, okay, independently set how, and they together come back to the same form essentially, that the Lorentz transformations in the spinorial space are nothing but the gamma matrices will form a representation of the Lorentz transformations in the spinorial space, and that is the reason why these wave functions, even though we started with alpha and beta matrices, okay, come out to be correct, essentially come out to be correct representations of nature. There are much more detailed very nice aspects about this thing related to spin and everything. We will see that in coming lectures essentially. Okay, I'll stop here and welcome. Thank you very much.